So here's a question, a physics question, and it has to do with energy in liquids and solids. A 25-gram block of ice is cooled to negative 81 degrees Celsius. It is added to 567 grams of water in an 89-gram copper calorimeter at a temperature of 23 Celsius. Find the final temperature. The specific heat of copper is 387 joules per kilogram degrees Celsius. That of ice is 2090 joules per kilogram degrees Celsius. The latent heat of fusion of water, that's what it takes to change it from ice to liquid or liquid to ice, is 3.33 times 10 to the fifth joule per kilogram, and its specific heat is 4186 joule per kilogram degrees Celsius. In this course it uses 4186. In many other places it uses 4184. I'm going to use 4186. Answer in units of Celsius. All right, so here is, I'm going to put, the masses in kilograms, since all those specific heats are in kilograms. So the mass of ice is 0.025 kilograms. The mass of water is 0.567 kilograms. The mass of copper, 0.089. In other words, I'm dividing the grams by 1,000 to get kilograms. The temperature, initial temperature of ice is negative 81 Celsius. The initial temperature of the water in the calorimeter, the copper, is 23 degrees Celsius. And here's the formula. The heat in the ice, the heat gained by the ice, has to equal the heat lost by the water plus the heat lost by the copper, the calorimeter. Now, the final temperature, I'm saying, is greater than zero. There's so much of that water and so much of copper that it's going to melt all that ice. So I'm saying that the final temperature is greater than zero. Nowhere in the question does it say that, but I have to put it in there. All right, let me find the heat of the ice. It's going to be this part first. I'll do these in red. It's the MC delta T of the ice to raise it from negative 81 degrees Celsius to zero, because now once it's at zero, it can start melting. And to melt, it's going to be the mass of the ice, which is still the same, times the latent heat of fusion, which again was given at 3.33 times 10 to the fifth. And then the ice is going to increase in temperature, and that's MC delta T again. The mass of the ice water, still the same mass, times the specific heat of water, times the temperature change, which is going to be zero, to get to whatever the final temperature is. So I'm calculating this. I put in 0.025 for the mass of the ice. 2090 is the specific heat of the ice, times 81. The initial temperature is 81. The final temperature in this phase is 0. 81 minus 0. I'm sorry. The final temperature is 0. The initial temperature is negative 81. 0 minus negative 81 is 81 degrees. So that's how I get that. That's to raise the water, to get there, or raise the ice, raise the temperature of ice from that negative 81 to 0. Plus, now here is the mass of ice, still 0.025, times the latent heat of fusion for ice or for water, 3.33 times 10 to the fifth. So that gets the phase change. Now, raising the temperature of the ice. The mass is still 0.025. Multiply that by the specific heat of water. I'm putting 4186 because everything's in kilograms. So kilograms, joules per kilogram degrees Celsius, times the final temperature. I don't know the final temperature because that's what I'm trying to solve for. So I will multiply these numbers together. I'm going to show this in blue. All of this stuff, multiply together and add it, is 12,557.25. And then this part, 0.025 times 4186, gives 104.65 T final. That is the heat gained by the ice. That has to equal the heat gained, lost by the water plus the heat lost by the copper. Well, here's the heat for the water. It's going to be the mass of water times the specific heat of water times the temperature change of the water. The mass of the water is 0.567 kilograms. Specific heat of the water, 4186 joules per kilogram degrees Celsius. And the temperature change in the water is the initial temperature, 23, minus the final temperature. The water temperature is going to go down, T final. And now I multiply these together. 0.567 times 4186 is this number, 2373.462. I just multiply those together times 23 minus final temperature. And now I distribute. I multiply that 2373.462 times 23. That's where this comes from, 54,589.646 minus 2373.462 times temperature final. And that's this part. All right, now I've got the water. Now here comes the copper. The mass of copper times the specific heat of copper times the temperature change of copper. Mass of copper, 0.089 kilograms. Specific heat of copper, 387 joules per kilogram degree Celsius. The change in the temperature of the copper, same as that for water. Initial temperature 23 minus the final temperature. Don't know what it is. I multiply these two numbers together, 0.089 times 37. Is it 0.089? Yes, 0.089 for almost like a 6. It's supposed to be a 0. 0.089 times 387 comes out to 34.443. And now I have to distribute that. Multiplied by 23, multiplied by T final. 792.189 minus 34.443 T final. So now, again, remind you of the formula. The heat loss, the heat gained by the ice is going to be the heat lost by the water plus the heat lost by the copper. And now I'm just plugging in these numbers. The heat gained by the water is this part, by the water. So that's this part. 12557 plus 104.65 final temperature equals the heat lost by the, which one is that? 54,589. That's for the water, the heat lost by the water, plus the heat lost by the copper. Now, everything with T final, this piece, and this piece, I want to get to the left-hand side. So I'm going to add 2373.462 T final. I'm going to add 34.443 T final. So it gets rid of them on the right side, puts them on the left side. This is just algebra. So it comes out to the 104.65 T final plus 2373.462 T final plus 34.443. So those are taken care of. Now I want everything else that doesn't have T final in it on the right side. I've got the 54,589.646, that's that one, plus 792 plus 0.189. Then I have to subtract this from both sides. So I'm subtracting it so that I can get rid of it on the left-hand side. So minus, there's the minus. That's gone. So now I have something that looks like this. And I can add these three together. 104.65 plus 2373.462 plus 34.443, and that adds up to be 2512.555. T final equals, I add all these three together, 54,589.646 plus 792.189 minus 12,557.25. That comes out to this part. And then I just divide. T final equals 42,824.585 divided by 2512.555, and that comes out to approximately 17.04 degrees Celsius. So this is the key that I have to know, that the heat gained by the ice is equal to the heat lost by the water plus the heat lost by the copper. And then just keep the phase changes in mind. Phase changes plus the temperature increases or decrease. The only thing that the water and the copper did was decrease in temperature. The ice had to both, first it had to increase in temperature, then had to do its phase change. And then it had to increase in temperature, this part, phase change, that part, and then increase in temperature some more after the ice all melted and turned into water. So that's it. There's the answer, 17.04 degrees Celsius.